All right, so my research spiel. Um, I have a couple different projects with other professors. I'm going to start talking about my own project though. What Sean's doing right now is calculating the change in energy for solvating a metal ion in water. So creating this aqueous system where there's a metal ion like iron 3 or lead 2, right? We actually put it in water, and then we use computational techniques to figure out what the total change in energy is for that process. We look at water by itself. We take water, we put a metal in it. The difference in energy is that total internal energy change. All right. The project is purely computational. We use an older language called Fortran. The way I see this project is it's just getting someone's feet wet in what a computational project looks like, just like what a pure theoretical project looks like. It is a classical simulation. So, what we're doing is we're not really invoking quantum mechanics at all, but we get to learn a ton of interesting techniques, and we get to look at some code. And even though it's an old language, you develop skills related to just what a code looks like in general, how you manage the data inside it, how you manipulate arrays, so on and so forth. It's just a really good sort of basic foundational process for what a pure computational project will look like. Along those lines, it is a classical simulation, but we do get to learn Monte Carlo integration. For next semester, I have a junior that wants to work on this project with me. So if a senior decides that they also want to work on it, I do have multiple avenues that we can go. The easiest thing to do, though, to figure out what this project is about is to take a look at Sean's presentation when we do our minds at work. All right. If you're interested in pure computational work, which I don't think there is any of you, but just in case, you can zoom into me. We can talk about it more. But like I said, it's using Fortran to do a classical simulation for water. All right. Using Fortran to do a classical simulation for a metal in water, and then looking at the energy difference. And the technique that we're going to use is Monte Carlo integration. All right. The next research project that I'll talk about, and probably the last one I'll talk about. I mean, usually I get hooked up with another professor when there's some sort of data analysis that needs to occur or some sort of modeling that occurs. So if you are talking to a different professor and there's that aspect that you'd like my help with, always reach out to both of us and I can help. Along those lines, Dr. Dan, he makes these complexes isn't the right word. He makes these organic compounds. And it's a synthesis project. But the interesting thing about these organic compounds is they have really interesting kinetics. Right now, they're hard to make, and it's hard to see the kinetics. But we do have a neat instrument that we're trying to kind of work the bugs out with that could get us to see, right, how these organic compounds that you synthesize with Dr. Dan, how they decay in water. So you throw these organic compounds in water, and what happens is you see some really interesting kinetics. So if we just kind of monitor the concentration of whatever that compound is here versus time, okay? We're used to seeing curves like from physical chemistry or even general chemistry where decay kind of looks like maybe an exponential decay, all right? Maybe it's an equilibrium decay, so it finally like ends up at some value down here that's not necessarily zero, right? But what we're used to analyzing with our first order differential equation techniques, with the techniques that we learned in physical chemistry, is just these types of simple kinetics where you see one type of kinetics. And what I mean by that is it looks like one nice smooth curve, right? For these guys that Dr. Dan cooks up, what you see and why it's interesting is you actually see two distinct sections where the kinetics look different. You see this very quick initial section where it looks like a really quick decay. And then after that, all right, and I'm just going to draw it in a different color, you see another decay, but the decay looks slower. So if this initial decay was followed for the whole entire time, right, it would die off real quick. But actually what we see is an initial drop and then a slow decay from there, right? So this is really interesting because not a lot of systems do this as far as we know. We say that it has two different phases. So there's a quick phase and there's a slow phase after. And so what we came up with was a way to attack this from looking at the mechanism. So Dr. Dan creates these compounds, and then there's a mechanism that we can say, okay, maybe this is occurring. How can we support this mechanism through kinetics? And that's where I step in and I say, okay, well, let's model this. Let's look at the actual mechanism in the context of kinetics, and let's look at the coupled first order differential equations. And that's what's different from what we've seen in PChem. We're going to look at coupled first order differential equations. And what we're going to use, though, is we're going to use the steady state approximation where it's necessary, right? We're going to use an equilibrium approximation where it's necessary. And what we do is we look at the mechanism and we use all those techniques that we learned in PChem, and we try to see, right, how we can get these two distinct phases to manifest. So my part of this project is, again, data analysis. It's a bit of modeling. We use MathCAD to model what's happening, right? You know, the reason we use MathCAD is it's just the software platform that we have, and it has the abilities to do this sort of thing. We could code it in Fortran if we wanted to. If that sounds interesting, you can let me know. But essentially it's saying, okay, let's model this. Let's use some approximations. Let's justify those approximations, all right? Let's use MathCAD to show how we can get information about the mechanism from this decay. The end goal here is, if we see this result, the modeling that I have is set up to be able to elucidate rate constants from each one of these situations. Individual rate constants for steps in the complicated mechanism, okay? And like I said, that chemistry part is more Dr. Dan. What the actual synthesis looks like and what the actual decay looks like from a chemistry standpoint, my part of the analysis is how do we deal with that from a mathematical standpoint, okay? So it's kind of interesting modeling. And again, it's first order differential equation techniques that are a bit beyond what we learned in physical chemistry, but they're not completely prohibitive in terms of how hard they are to understand. And then we also use some things that you are familiar with, like steady state approximation and the equilibrium approximation. All right. So that's my role in Dr. Dan's research. If you are interested in that sort of project, kind of reference both of us, talk to both of us, come up with questions. I'll write this down. I know I mentioned it before. But like if there's something that you run along or run to, and there's like modeling that needs to be done or data analysis that needs to be done, you can bring me into that. You know, I work with Dr. Richardson a lot for his projects, just because he always comes up with some really interesting data, and then we can look at, you know, different modeling of that data, how we can pull information from that data, right? So there is some flexibility that I have where if there is some sort of theoretical component to work that's being done and I kind of can get pulled in on that, you just kind of got to let me know and I can help you out with that end of things. But in terms of the main projects that I have going on right now where I know there's a bit of availability, it's my project number 1 where it's just pure computation work, and project number 2 where we kind of come in on the back end and we try to analyze a kinetics experiment to get actual mechanistic information from it. Okay. As always, if you have any questions, email me. We can talk over Zoom. All right. Whatever you need, just let me know.